Hi. Today we'll be discussing load flow analysis. Now, the idea of load flow analysis is you want to analyze a circuit. Let's say this circuit. In this circuit, I have two machines. Probably one of them is a generator. Another one may be a motor. Other one may also be the other one may also be a generator. And then I have a load that is denoted by its power, real power and reactive power requirement, interconnected through three buses and three lines. I have this bus 1, bus 2, and bus 3, line 1, line 2, and line 3. Now, load flow analysis, as I have said, is used to analyze the circuit to know how much power, how much load is going from this. Let's say if this is a generator, from this generator to the system, how much power is flowing in this line, maybe going this way, this line maybe going that way towards the load, going this way towards the load. If this is a motor, probably it's going this way. If this is a generator, it's going this way. This one may go from this way, may go this way. So we'll know that using load flow. That's basically load flow analysis. In your lower EE, you'll be solving this using your KVL, KCL equations, your mesh analysis, your nodal. That will depending on what's the given parameters, what's the required output, you'll probably get how much current are flowing in the branches, how much voltage are there in the nodes. Now, since load flow deals with the flow of power, with the flow of loads, therefore we are interested with two parameters. We are interested with the voltage and current. We are actually solving for the voltage and current at the same time, simultaneously. And the solution for that provides some complications in terms of load flow. I'll show you that. Okay. I'll be using this example. I'll be using this. Okay. Now, let's say that I have this system. Okay? Let's focus on the power injection at bus 1. Let's focus on the power injection in this bus. I'll zoom in this bus further. No, later. Okay, so let's focus on that bus. Now, that bus has two lines connected to it and a machine. Right? So if we talk about current injection, you may want to convert this into current source, since we'll be talking about KCL in this from this moment on. So if that is a current source, so what will happen is that I'll short this internal impedance to the load, and I'll have a current source connected to it, at which the current at this current source is equal to the internal voltage. Let's call that EG divided by, so that's EG divided by 0.1. So that's J 0.1. So that's basically your current there. So yeah, I'll draw that way. So now I have a current injection going through bus 1. So this current injection is equal to your currents going out by KCL. And this currents going out, this current, this one, is equal to V1 minus 0 divided by J 0.1. I'll be using J here. I haven't written that J there. Now this current, the current at line 1, that is equal to V1 minus V2. Take note, that is V1 minus V2, not V2 minus V1 because of the direction. It assumes that 1 has a higher potential than 2. Divided by Z12, and then this current Z12, yes, and then this current is V1 minus V3, again V1 minus V3, not V3 minus V1, because of the direction. It goes from 1 to 3, assuming that 1 has a higher potential than 3, all over the impedance between 1 and 3. Now the impedance between 1 and 2, the impedance between 1 and 3, the impedance J 0.1, the inverse of that, or 1 over Z of those lines, of those impedances, is just equal to 1, as to Y, sorry, to the admittance. So that means instead of writing it as V1 minus V2 divided by Z, I can write that as V1 minus V2, sorry, times Y12. Instead of V1 minus V3, I can write that all over Z13, I can write that as V1 minus V3 times Y13. Now I have a messy PowerPoint here. Okay. So now, my equation, sorry, my equations would be, for line 1, that would be this one. For line 1, that would be V1 minus V2 times Y12, plus for V2, that is V1 minus V3 times Y13. And for this current, that is plus V1 minus 0 times, let's say that is Y10. And this whole equation is equal to your current injection at bus 1. Now, most of the time, we know this current injection because we know how much voltage is in your generator. Yeah, or you want a certain voltage in that generator. That's why most of the time you already know that that I1. So that gives you an impression that your unknown here in this example is probably the voltages, and actually that's what's really happening in load flow. But yeah, I'll get to that. I'll get to that later. Okay. For, let's say, I'll give you another example. For this load, how are we going to do current KCL in this branch? I can convert this load into a current injection. Now, this P plus JQ. This is not like your generator that you can source transform. But for the meantime, what will happen is we will assume that this P plus JQ is a current injector. It is a current injector, such that it injects a negative current. It injects a negative current, or it takes away current from the bus. So now I have this current injection that is going out of the bus. So in this case, let's call this I3 since it is connected in bus 3. That makes this I3 equal to, let's say that these are the currents going into the bus. So since it is going into the bus, therefore this is assuming that V1 is voltage is of higher potential than V3, and V2 is of higher potential than V3. That makes this current equal to V1 minus V3 all over Z13, or V1 minus V3 times Y13. And this current equal to V1 minus V2 minus V3 divided by Z13, or this is V2 minus V3 divided by Z23, or V2 minus V3 times Y23, and that is equal to your I3. Now you do the same, and then you'll end up with this. You'll end up with this matrix. So what if I know this matrix? As you can see in this matrix, you have three equations. So now, since you have three equations, that gives you an impression that since I have three equations, then probably I have three unknowns. And that's the thing with power flow. Power flow deals not with the flow of current, but with the flow of power. Therefore, you are not really looking at, you won't be looking at current injections, but instead you will be looking at power injections. So if I have this equation, whole matrix equation, wait lang. So for me to convert this matrix equation into power flow equations, into power injection equations, so I need to multiply this whole matrix into a matrix of V1, V2, and V3. However, take note that S is equal to V times I conjugate, and that is equal to P plus JQ. So that is how you solve for S. So you cannot use V1 times I1, but instead you have to use V1 times I1 conjugate. So that makes this whole matrix conjugated. So to avoid conjugating this whole matrix, we'll be using S equals V conjugate I. So the only difference of that with VI conjugate is this will be equated to P minus JQ. So that means instead of conjugating this whole matrix, you'll just multiply this by V1 conjugate, V2 conjugate, and V3 conjugate. So what's the implication of that? The implication of that is, instead of current injections I1, I2, and I3, this will be equated to S1, S2, and S3, power injections. And this whole term is multiplied here by V1 conjugate, V2 conjugate, and V3 conjugate. So, sir, where is the complication? Where is the complication in this? Where is the problem in this matrix? Now, as I have said before, you have three equations. That gives you an idea that you'll be solving for three unknowns. And from the looks of it, I have three unknowns, V1, V2, and V3. However, because of the conjugate, I cannot say that V1 is equal to V1 conjugate. So instead of having three unknowns, you actually have three equations but six unknowns. And for you to solve that, you'll be needing to estimate the values, and that's basically how load flow works. You cannot really solve for this system directly, because you have this is how this equation will look like. I have in this scenario, uh, I have S2 S at 2 equal to Y matrix times V matrix times V2 conjugate. If I remove this V2 here, if I remove that V2 here, that will be V2 conjugate times Y21 V1 plus Y22 V2 plus Y23 V3 equal to S2. So that's how your power flow equations will look like. You have 3 equations for 3 buses, but 6 unknowns because of the conjugate, and that complicates things because you cannot use your linear system analysis for solving that. So instead, what we will do is, okay, I'll put some value for V1, some value for V2, some value for V3, and then I'll look into the power flow. If these are the values of V1, V2, and V3, how does the power flow look? Does it look realistic? Does it look practical? Then in my next iteration, I'll do the same thing, but I'll adjust V1, V2, and V3 by some value. Maybe move the angular displacement of the voltage by some degrees, or increase or decrease the voltage magnitude by some value. Then perform power flow again, and then look at the power flows if it's realistic enough, if it's correct. Now, that's basically how you do load flow. So that's why in load flow analysis, we'll be using Gauss-Seidel, Newton-Raphson, and then provide some more assumptions to reduce this Newton-Raphson into. I will be discussing this load flow probably after, but yeah, these are actually estimation methods. So yeah, that's load flow analysis. That is estimation. So you'll be guided by the type of buses in your analysis. I'll be discussing that later. Then yeah, I guess more discussions will follow in the following videos, but that's the brief overview of load flow analysis.